different sheet. Today, we're mostly going to be using those formulas there. So hopefully you have memorized tangent is sine over cosine, cotangent is cosine over sine, and then the cosecants, secants, and cotangents, and then the Pythagorean identities. And you need to know how to adapt the identities. So this first one can be written three ways. It either equals 1, or it equals cosine squared, or it equals sine squared. So I could say sine squared cosine squared is 1, or sine squared is 1 minus cosine squared, or cosine squared is 1 minus sine squared. So those are really the big ones that we're going to use today. And again, there are an infinite number of ways to prove these. Most of them are really difficult, and there are a couple ways that are easy. So if you start into it and it looks too hard, change your tactics. And I do apologize, but really the only way to get good at this is to do a lot of problems. And you have to know this to move on. I mean, this might seem like a non-important chapter, but this is huge in calculus. You do this all the time in calculus. All right. Are there any on the front page you want me to work? Six? Okay. 6 is one of the ones that ends up being too hard if you only work on one side. So now I'll let you work on both sides, and whenever you have two fractions, your best option is to cross multiply. So if I have 4/6 equals 2/3, that's true, right? If I cross multiply, I get 12 equals 12, which is also true. So if you have two fractions, cross multiply. It wouldn't do you any good on, say, this problem. If you cross multiply, you're going to get what you started with. And if you looked at number 2, cross multiplying is not going to do you any good, because you cross multiply and you end up with exactly what you started with. So we cross multiply secant squared of theta plus 1 times secant of theta minus 1. Oh wait, there's no squared. Equals tangent squared. And eventually I just stop writing the thetas, because there are too many of them. What do you notice about those? What's the word? They're opposites, called conjugates. They're called conjugates. What do we know you get when you multiply conjugates? Difference of squares. So I'm supposed to multiply them out like that. But what do you notice about this term and that term? They're going to cancel. Whenever you have conjugates, the two middle terms cancel. So as long as they're conjugates, all I have to worry about is first term times first term and second term times second term. So secant squared of theta minus 1 equals the tangent of squared of theta. Is that on the reference sheet? Well, not really. It's on your hexagon sheet. But if you look at the red reference sheet, what does it say? Tangent squared plus 1 is secant squared. So if you move the plus 1 to the other side, then it matches, so that is true. So when you cross multiply, you're just trying to come up with an equivalent statement. And these are equal, so we're done. And if you're allowed to cross multiply, it does make things a lot easier. Okay, pick a new one. 13. All right. Let's see, what do I want to do? Do you see any of those on the reference sheet? You could, yeah, that might be the way to do it. But what I want to point out is up here on half-angle formulas, don't get 1 minus cosine of 2 theta mixed up with 1 minus 2 cosine squared of theta. Do you see the difference? So number 13, don't get it confused. There's no good way to do that. Don't get it confused with the half-angle formula. There's a difference between 2 theta and squared theta. So don't make that mistake. Don't use the half-angle. So let's try Hannah's method. It may or may not work. And really, the only way you're going to get good at this is if you try it a whole bunch of times. So, sine over cosine minus cosine over sine. What should I do to put two fractions together? I just converted tangent and cotangent into sines and cosines. What? Common denominator. What is the common denominator going to be? Cosine sine. So what does the first fraction need? A cosine. So cosine sine minus... Wait. It needs a sine. I'm sorry. Sine cosine minus... Oh my goodness. Sine squared minus cosine squared. Well, do you see any of those on the formula sheet? You don't see sine? Right, okay, good. Sine squared plus cosine squared equals 1, but we don't have that, so don't use it. Okay. What about... Oh, good. So this looks kind of like what I want it to look like, correct? This is right. Those match. So all we need to do is adapt the top so it works. Well, I have one negative cosine squared. If I could create another negative cosine squared, then I'm even closer to the answer. So can we adapt the sine squared? Look at your Pythagorean identities. Maybe. Oh, I went. Sine squared plus cosine squared is 1. So sine squared is 1 minus cosine squared. So I change this 1 minus cosine squared. 1 minus cosine cosine squared over sine cosine. Is that what I was looking for? Put the cosines together and just put a 2, and we did it. Good. All right. Turn it over to the back. Look at the last 4. I'm going to give you a hint. The last 4 may or may not be true. So you can assume that all of them are true except 30, 31, 32, and 33. They might be true or they might not be true. The last 4. So let's do the last one. Okay. Which side would you rather work on for the last one? Okay, it's usually easier to convert fractions into non-fractions than it is to create non-fractions into fractions. So you're probably better off doing the left side. But again, we might get so far and realize that it's not going to work, and then we need to start over. So I'm going to convert this. 1 divided by 1 over the cosine times 1 or times sine over cosine. That gives me 1 over sine over cosine squared. Flip and times, right? So I flip this upside down, cosine squared over sine. Anybody confused up to that point? Kelsey, where'd you get lost? It's the reciprocal identity. On the third column on your reference sheet, second section down, secant is the reciprocal of cosine. Okay, so now I have cosine squared over sine squared. I could turn that in, or just sine. I could turn that into cosine over sine times cosine, which would be cotangent times cosine. But does that get me any closer to my answer, which has a subtraction in it? No. I need to generate a subtraction somehow. So that's not going to work. Well, can I turn either of those into something else, preferably something with a subtraction in them? 1 minus sine squared. So I'd have 1 minus sine squared over sine. Now, here is a very useful trick. This is something you've probably never done in math. You've done it one way, but you've never done it backwards. Let's say I had, my goodness, a over 4 plus b over 4. Can I put that together? Yeah, a plus b over 4. That is the simplified version. Well, if I had let's do 4 plus a over 8. Can I unsimplify that? I could do 4 over 8 plus a over 8, which is the same as 1/2 plus a over 8. We're going to refer to this as splitting a fraction. So simplifying is using a common denominator to combine a fraction. But if you have a simplified fraction, something plus something over a common denominator, you can always go backwards. And this is going to be used a lot, not every time, but it's going to be used quite a bit. So let's split this fraction. 1 over sine, which is equal to the cosecant, minus sine squared over sine, which is just negative sine, and I'm done. What's that? Well, I wanted to do one that worked first, so that I could show you one that doesn't work. Okay, let me show you one that doesn't work. Let's do 30. I'm going to pick the left side for no real reason. They look equally easy in my book. What would you do with those? Just convert to sines and cosines. Cosine over sine plus sine over cosine. Now what? Well, you can only cross multiply if there's an equal between them. If there's a plus, we need common denominators. So I'm going to put an extra cosine up here and an extra sine up here. So I have cosine squared plus sine squared over sine cosine. Yeah, that would probably work. I think it would be hard because, so she asked, it says cotangent plus tangent, and our answer is cosecant times cotangent. And she's saying, well, we already have a cotangent, why don't you leave it the same? And you probably could. My guess is it would be hard because turning an addition into a multiplication can be tough. Because you end up having to factor or reverse factor, one of the two. So that's not something I would do. If you can make it work, great. All right, now what do we do? Would doing a fraction split make sense? Why not? We just put it together. So you don't want to do a fraction split when you just found a common denominator. It's like factoring and then multiplying the factors back together. It doesn't do you any good. Okay? Can we convert to secants and cosecants? Would you recommend it? I wouldn't recommend it. What should we do? No, don't go to the other side. You're almost done. When you get stuck, look at the reference sheet. Good. We could put cosine squared as 1 minus sine squared. There's an even easier way to do it. What about this? It equals 1. Sine squared and cosine squared added together equal 1, no matter the order they're put in. So we end up with 1 over sine cosine. Now what should we do? Well, what am I looking for? Cosecant, cotangent. Do I have a cosecant? 1 over sine is the cosecant. So this is cosecant. What is that? Secant. So I actually have cosecant times secant. Well, so can the cosecant times the cotangent equal the cosecant times the secant? It can, as long as can A times B equal A times C? If B and C are the same number. Are B and C the same number? No. Therefore, this one is impossible. We almost got the answer, but these are not the same thing. Every once in a while they will be. The cotangent graph and the secant graph will cross every once in a while. But having said that, they're not always the same. So this one does not have a solution. It is not an identity. Okay. I haven't worked the other two. I don't know yet. But, I mean, look at 28. 28 is so easy. Cross multiply, and you end up with sine squared equals 1 minus cosine squared, which is an identity on your reference sheet. Well, it just needs to be adapted a little bit, but it's on there. Look at number 27. 27 looks really tough, but it's not tough. It's really easy. Okay? If I had x squared minus y squared, can I factor that? X minus y times x plus y. It's a difference of squares that factors into conjugates. What if I change those 2's to 4's? X squared minus y squared times x squared plus y squared. So 27 is going to be cosine squared minus sine squared times cosine squared plus sine squared. Oh, that's really convenient. What do you notice about those two factors? One of them is the answer, and the other one equals 1. This one matches that one, and this is the Pythagorean identity that equals 1. So we're done. Okay? I promise not to give you a test until I think you're ready. Does that make you feel better? And I do think that this will be the last test of the year. So it's not going to be until after the core test. So we're not anywhere close to it taking a test. So I'm not going to leave you in the dust. Thanks for telling me that you're kind of confused, Flor. Well, that's good to know. So I'll slow down. Okay. So get to work on this. Ask lots of questions, and don't get frustrated when you get stuck. Just try something new. Good luck.